Now you first did optimization problems, max-min problems back in grade 11. And you mainly did them with parabolas. Do you remember some of the parabola questions you had back in grade 11? There were the questions that said, they gave you in a formula and a rock is thrown up in the air and it follows this parabola. What's the maximum height that you had to find? And you always had to find the vertex, right? The vertex of the parabola. Or you might have had those questions where a farmer was building a fence alongside of a barn. And what is the maximum area that that farmer can make with a certain amount of fencing? And you'd set up an equation, it'd make a parabola, and you'd have to find the vertex. We're going to do the same thing, but now instead of having to do what we used to do with finding the vertex by completing the square and changing it to vertex form, we can use our calculus because we know when we have a maximum, the slope of our tangent is going to be equal to 0. And that's going to help us find it. So anytime we want to find a maximum or minimum, we're going to find our derivative, have it equal to 0 because that's where we know our maxes and mins are, and then we'll be able to solve our equation from there. And once we've got that information, we'll put it back into the context of the question and be able to answer that question. So here's just a reminder of how you used to solve it. I put a formula for the axis of symmetry, or the x-coordinate of the vertex. Had you ever seen that formula before? So if you have any parabola, well, I guess I can make it equal to y. If you have any equation of any parabola, the vertex will always have that as the x-coordinate. If you complete the square, you'll be able to see that. Okay? But the problem is even if you've seen this formula before, chances of you remembering how to do it or remembering that formula, chances are you're going to forget it because you're not going to use it very often. It's another amazing thing about calculus is it's not hard to find a derivative, and it's not hard to set that derivative equal to 0. So all of these other techniques that we've learned over the years that you may have forgotten or have to review a little bit, the calculus technique is very powerful and, for the most part, easy to remember. So here's our ball thrown upwards. It is not on the planet Earth because there's not the right gravity involved, but we're not worried about that. So here we've got an equation, y equals 15t minus t squared. And we're going to figure out when it's at its maximum height and find the value of y at that time. So if we find our derivative and we set it equal to 0, we find out that that happens at 7.5 seconds. If we want to find out exactly what that point is, well, we know the time is 7.5. We can plug 7.5 back in to our original equation. (15 times 7.5 minus 7.5 squared and we get 56.25. So as far as this is a question. Now, what does that mean? Well, the ball reaches a maximum height of 56.25 meters at 7.5 seconds. Other things we could have done as far as connecting this to curve sketching. Well, if you did put 7.5 and check before 7.5, this is going to be positive and going up. After 7.5, it's negative. So you could really tell that 7.5 was the maximum point. We'll do one more. Fred wants to enclose a rectangular parking lot with 60 meters of fence. So this is one that you did back in grade 11. There's a building on one side of the lot, so from the top view, he wants to make a rectangular parking lot, enclose it with 60 meters of fence, because that makes a lot of sense. That if you have a parking lot, you want to fence it in so no cars can get in or out. It's a good strategy. And there's a building on the other side, so they can't get out that way either. Perfect. Now, if you have 60 meters of fence and you're setting up as a rectangle, one possibility you could do is you could make it 1 and 1 and 58. Not a very nice parking lot, because most cars wouldn't fit in there, but that is a possibility. That would give an area of 58 meters squared. You could change these numbers. You could go 2 and 2, that would take away 4, and then there'd be 56 here. So if you're ever having trouble figuring out how to set this up, start writing a couple numbers down. Because once you write a couple numbers down, you start to realize, what am I doing? If I'm picking a value here and here, okay? So once you've done it with a couple numbers, you say, well, what don't I know? I don't know the dimensions. I have to pick x for something. Can you see that it makes a lot of sense to pick x for those sides because you have 2 of them? Then how did we always figure out what would be left? We subtracted those from 60. So now we've taken our idea and we've applied it to algebra, and now we've set up an equation. Or we've set up a diagram. We can set up an equation for our area, because our area is just length times width. So we have 60 minus 2x is our length, x is our width. If we multiply that out, we get 60x minus 2x squared. Again, that makes a parabola. If we want to find the maximum area, now we can just find our derivative, set it equal to 0, and solve for x to get x is 15. Now that x is 15 isn't our maximum area, that's just one of our dimensions. The question says find the maximum area, so the maximum area would be, well, if we had 15, it would be a 15 by 30, which is equal to 450 meters squared.